we have a cost function we're going to call J. It looks like this. And we'll have the state vector times some matrix Q times the state vector. Well, that's quadratic. We end up with some squares in there. Right? We have the input vector, U, transpose, times some matrix R, times U. That's quadratic. And then we end up with the cross terms. They're quadratic as well. Right? So here's the quadratic part of the linear quadratic regulator. And then our cost function has a quadratic form. Right? And basically what we're doing is this is penalizing these states from being away from where we want them to be. Right? So we are trying to regulate the states of the system, in this case, in this basic formulation, to 0. We don't want x to move from its equilibrium position, x1. We don't want x2 to move from its equilibrium position in this example. Right? Or we don't want x1 dot or x2 dot to be non-zero, meaning they're moving. So our objective in this case is to keep that system stationary, let's say. Right? Even if there's some other force that comes along and pushes on it. Okay? Really, as a designer, what your choice here ends up being is picking out for this control method the knobs you get to turn as a control engineer to make this work well is picking out the terms inside those three matrices. Okay? And more importantly, in many cases, is picking out the relationship between the terms in the matrices. Right? So for example, let's think about this. If the values of this inside this Q matrix are really high relative to what's in the R matrix, what are we telling the controller to do? So Q has really large values in it. R has really small values. So which thing contributes more to our cost? The larger one, right. So if Q is big, right, in particular if Q is really large, then whatever's happening to my states adds a lot to J. Right? And if I'm trying to minimize this, that means that these kind of matter more. I'm valuing where those states are changing more than I might be my input. Okay? If R is really, really large, right, then any kind of control input adds a lot to my cost. Right? It starts penalizing. So I worry a lot about my actuator effort. Right? And then actually, it turns out we don't really use this N term so much, actually. Right? So quite often you'll see that the N is 0. So we can get by with just Q and R. Okay? And by picking the values of this. So in this case, for this problem, right, we have let's just look at Q to begin with. The first part of this, right? So this matrix has to be 4 by 4 in this case for the matrix multiplication to work out. Okay. Quite often, you might just have terms on the diagonal. Okay. And so we can pick Q relative to R. We also can pick like Q1 relative to Q2 or Q3 relative to Q4. Or take the kind of, what should the values of these guys be? And again, the kind of relationship between them tends to matter more than the absolute number. Okay. So if Q1 is larger than Q3, what are we telling the controller to do during the optimization process? Will the controller care more about the position of x1 or x3 or mass 2, m1 or m2? Yeah, if q1 is much larger, what we're saying is, hey, the position of x1, our first state, is more important to us than the position of x3. Right? Let's write this out. This might help. We end up with that for that term, right? So if we pick Q1 to be much larger than Q3, we're saying we care about our first state much more than we care about the third state. Or we care about the position of M1 much more than we care about the position of M2. And we can look at, well, we think about the controller, right? What the solution is going to do is give you basically, and we won't go through the math, we don't have time. You'll end up with a controller that has this form. Turns out we know how to solve this quadratic function, this quadratic linear program for us. We can get a matrix called K. This is the gain matrix, and it multiplies our state vector. Okay? So if we really value our states, right, that's kind of like cranking up the gain on position. Something like that, intuitively. If we really value Q2 and Q4 in this case, the velocities, that's something kind of like turning up the derivative gain on a PID controller. Right? Because I care a lot about the velocity error now. So velocity error is more important than position error. So I can increase its contribution to the control effort. There is, let's see if I can do this quickly. Put down. Okay. What I will do, okay, so here's one of the, just kind of in case you have never seen these before, this is called a Jupyter notebook, and what it allows us to do is actually write code inside a web browser. So you see I'm actually in Safari on my Mac. And it lets us, this thing is pretty cool and useful for your learning things maybe. I use a lot in my classes at UL, Lafayette. We do a lot for our research as well, kind of initial exploration. So what it lets you do is put, for example, figures and equations right in line with the code you're running to implement those figures and equations. So it ends up being a pretty useful system, I think, for us. So in this example, what I have is a little bit different model, right? So I have an input Y, so I can control the position here, a spring and a damper, and a mass that has X on it, and then some kind of disturbance force F. Okay? And I can write the equations of motion of that system. And I get this guy. And then I can write, basically, start breaking that down into a system of first order differential equations, which I've written here. So that process we won't go through in a whole lot of detail, but basically exactly what we just did for the system that's on the board behind this. Okay. And then I'm able to simulate that system and plot its response for some kind of input. Okay. I mentioned you can also do the system. So I took that same system now, and because it's linear, I can write in really this state space form. In this case, I am using W instead of X to avoid the kind of confusion with having 6 different X's all mean different things. All right. So I have a state vector W. I can define A and B. And once I've defined A and B, I can kind of here I'm doing it in the code. So here I'm doing it in the code. And I could do something similar to how you would do it in MATLAB. So in this case, the Python Control System Toolbox, just like in MATLAB, has a function that's SS, which stands for state space, and you just give it the 4 matrices that represent your system. All right. So I have some system. I'm going to use this function that comes with the Control System Toolbox, give it those 4 matrices that describe my system, and now I have an object that represents my system dynamics. And I can use that to simulate the system, which I'm going to do. Right. So in this case, in MATLAB, this function is called LSIM, but basically this is like LSIM in MATLAB. So I give it the system, the time, and then my inputs. And then it handles running the simulation and saving the data for me. Okay. And then I basically, all this code here is to make my plot look pretty. And I get to the same plot I had before by solving the differential equations manually. Okay. If I have those A and B matrices, I can do this LQR idea. Right. So we saw, basically I want to choose my control input to be some gain vector k times all my states. Right. You'll see that this kind of controller is called full state feedback. Right. So in order for this to work, I have to be able to measure every state of my system. Right. Are you ever going to be able to do that? You have a system that's there. I can measure position and velocity of every linkage perfectly. Well, I think it's going to be very rare that you can do that. I'm hesitant to say never, but it's going to be very rare that you can measure every state of your system. Right? So this formulation quite often ends up being you're going to have to estimate some of those states. But we're using them all for now in simulation. Right? So here's kind of the explanation of this again. In this case, I've defined, let's look at a few different responses. I've set my Q, and I've put Q1 to be 1,000. So I care a lot about the position of X1, or X in this system, and only a little bit about the velocity. All right, so for this particular system, that force, scroll back up to the top. So what we're going to look at is I want, no matter what this force is, I'm going to try to move Y to make sure X doesn't move. Right? So basically my controller is trying to pick a Y so that the spring and damper force balance out any kind of disturbance over here. Okay. And what I'm saying for what I'm telling the LQR controller to do is I just care about the position. I don't really, at least so far. I don't care so much about what its velocity is, but keep its position here. Don't let it move. Okay. So let's scroll down. So there was the control without that. Turn on LQR. And then basically we end up with a plot that looks something like that for a solution. Okay. So I have some kind of force disturbance. It's just a kind of pulse, kind of hit the mass. And then you see that Y moves quite a lot in order to try to keep X still. Okay. Let's go back up and change that Q matrix and see what it might change about this result. So maybe I care about the position even more. So let's add another 0. Let's add 2 more zeros. All right? So I really want to make sure X is staying still. Okay? So now you see the scale changed a little bit, but actually how far X moved did decrease. But in order for that to happen, you see that Y, the blue line, really gets big now. Right? It's trying to move more so it can generate force to exactly cancel out the pulse now. Right? Which makes sense. I'm valuing how far X moves more than Y. Okay. Let's go back up. Go back to this formulation. Well, what happens if I maybe turn up and I start caring about the velocity of X too? Right? It's kind of like, we talked about that, if the velocity of x is kind of like adding damping maybe to my controller, my derivative control. So hopefully that's going to damp out a little bit further. Okay. So my text kind of messes up, but you see, we get kind of around the same peak, but less oscillation once we get back to where we were. It's not bad. Right? If we went the opposite direction, and say I don't care about the velocity at all, maybe that's a 0. And you see I get back to having some oscillation, now that I say don't worry about velocity so much. Okay. In this case, I also could put some value on, because of how I define this system, y actually shows up in that Q matrix. Put some value on it, and now you start to see we start limiting how far y is actually able to move. So now we're not going to 3 meters anymore. We care, we're saying, hey, I care about how far I have to move y. So it gets smaller. And as a result, x moves farther because I can't move y as much to stop it. Right? So basically what I'm trying to show is just by picking those different parameters in that Q matrix, I can kind of value performance in one state versus the other. And there almost always will be some trade-off between those things. So there's some skill and some art in control design and picking, for the LQR controller, picking out what those Q values are. Right? Just like in PID control, there's some skill in picking out what P, I, and D need to be to work well. Okay? All right. So let's do this again. Get that out of the way. I want to talk about one more formulation of this. It's kind of an extension of this idea. Oh, that's actually a mistake. So, actually, let me correct the mistake first. This is not a T here, that's infinity. For that to work, sorry. Okay. So I take the cost from now until forever. I consider that as part of the control design. Okay. So that's LQR. Let's look back, we can erase this part. Well, there's another formulation of this that's really similar. So we look at this infinity, we can call this infinite horizon optimal control. So I'm planning out from now until infinity. Right? Well, we don't really know what's going to happen with our system, or maybe even care what happens with our system between now and infinity. Quite often we care what happens with our system between now and 1 second from now, or now and 10 seconds from now. Some kind of finite horizon. So what I can do, instead of solving 0 to maybe some kind of capital T instead, where T is less than infinity. And I have this same stuff. We don't have time to rewrite it. All the same stuff is in there. Right? So what I do is I take and I solve this controller, and I'll get, during this, I minimize that cost. Right? I'm trying to pick U. To minimize the cost there between 0, where I'm at right now, and some time in the future. Okay. And what that's going to do basically is give me some kind of control input as a function of time. Okay. And what I'm going to do is take that now, and I'm only going to do my start time, start 0. Okay? Then I'm going to take my system and resolve this optimization problem between, now I'm at time t, I solve this out until time t, and look between t and 2t, my next time maybe I care about, and that solution is going to give me, let's call that one, some new set of control inputs. Right? And that's going to be true between t and 2t. Okay? And I'll only take the first value of that answer. Right? This gives me a whole function for time. Right? And I take the first one, and I keep repeating this and repeating this and repeating this. Okay? So what happens at every time step now, rather than solving this once and kind of assuming your system never changes, right, I can take and solve this problem at each time through my control loop. So I can take and measure my system. I know the trajectory I want to be on. Right? Resolve the optimization problem. Get an optimal input for my system, but I only do the first part of it until I take another measurement of my system. I take the measurement of my system now, resolve the optimization problem to figure out the optimal input to push me towards where I want to be. Okay? Once I resolve, I get some kind of new optimal control input, but I only do the first part of that, the part that's valid for right now, until my next measurement. And then I get another measure of my system, and I resolve the system, the optimization problem. And now I have another optimal input that's valid between now and whenever, until my next measurement. And I keep doing that and keep doing that and keep doing that. Right. And basically this whole method, what I've summarized at a really high level, is kind of the basis called model predictive control. And it's called model predictive control because what I'm doing actually is I'm using some model of my system to predict the cost into the future. And using that prediction to pick then what the optimal input for right now should be. So I know between now and sometime t in the future, I have some optimal input. So rather than just measuring my states, I'm using some prediction into the future to pick my current control input. Right? And I just repeat that every time I get a new measurement for my system. This idea has been in use. It was first developed by Shell, the oil company. And it worked really well for them because most chemical processes are kind of slow moving. Dynamics are kind of slow. So I have plenty of time to solve this optimization problem. What's been really neat is recently, computers are a lot faster, right? So this started in the 1980s, right? Computers are so much faster now, we can actually solve this optimization problem in real time for real robotic type systems, real automation systems. Right? A lot of autonomous car control. This is kind of common in that area. I have a project in my lab that's autonomous self-driving boat. We are using this to pick the navigation path for the boat. Right, we can predict forward in time what's happening and map our trajectory that way. It's pretty cool. Okay, so let's put this one more down. I got one more extension of this for you. So far what we've done is basically use some direct math based on a cost function that we decided. Right? Well, that requires some amount of skill for us to pick out what that cost function is. Right, we have to know what it is. And we have to decide that cost function based on maybe something that's not directly in that format. Right? It'd be nice if we had some kind of method to actually just take the result we want and kind of give that some kind of score, how far you are from that. Right? So I'm going to look over. Where is he at? Okay. And one way we can do that is have this idea where I'm just going to try a bunch of random stuff, right? I'm going to try, I have a system here, and I have a simulation of it, a good model. And I'm going to start out, I have some kind of signal that will give it a reward if it does a good job at something. If it gets close to what I want it to do, it gets some points, basically. And I just try random stuff and figure out, basically from all these random trials, what gets me the most number of points. Right? And I can use from each one of those random trials, I know my input, I know the reward I got, I actually can differentiate that back in time to change my action. So my action becomes less random over time. It's quite interesting. So here actually is a system. The system here is actually kind of a simple crane, right? And it's trying to move this payload over to this bullseye. And I haven't told it anything other than it's going to get some high score if it gets closer to this bullseye. Okay? And this phase right now, it's just trying random stuff. Right? And you see it's not working so great. Over time, however, after thousands and thousands of times through this, it starts to figure out what it would take, or what it does take, to get to the answer, to start moving towards that target. Right? It's using some reinforcement from the points it earns to decide its next control action. Okay? This is really popular. Let me change inputs. Maybe it's here, sorry. I had this all together a few minutes ago. Okay. So here's another kind of a little bit of a toy problem, maybe. And the objective of this is just to keep this bar upright. And what this started as several thousand trials ago was this system knew nothing about the rules of this game, knows nothing about the model, nothing about the dynamics of this inverted pendulum. Right? And it just basically, it's getting a score. This is set up where it gets some kind of reward if the cart stays upright, the pendulum stays upright. And by doing that process over time, and thousands of times, it learned how to keep the cart upright. Okay. So this idea we're talking about, basically it's called reinforcement learning. Right. Reinforcement learning is a big part of the Google team that beat the world champion in Go, is using reinforcement learning. Right? A while back, the chess one did not. There's also, let me see if I can pull it up. It's not going to work so well, probably. Also, it's kind of one of the most famous recent papers in this. Actually, used this reinforcement learning idea to learn how to play Atari games, like old school Atari games. Right? And basically, the system knew nothing about the rules of the game. All it knew was the score it was accumulating. And basically, you just run this and run this and run this for hours and hours and hours, it figures out how to play the game. And the trick is you take that reward signal, and that reward signal you're getting, the points you're scoring or the points from my crane, get to telling us how we should start changing the inputs. And the system learns that. It's pretty interesting stuff. I think this is going to be a big area of controls work in the near future. There's a kind of really interesting group at California, Berkeley, that's using it for robotic grasping. So it learns how to pick some objects up based on lots of simulations. Kind of works pretty well. The crane you saw That example for the crane, I think I don't. Let's see if that's going to work. So the crane example, hopefully this works. Does not. Okay, sorry, I don't have time to figure it out. Anyway, the crane example you saw, which is kind of interesting and why I'll actually add another piece of code to the website. What was really interesting for us, we started working on this problem, is that this reinforcement learning got to an input shaper. So that's been a really interesting part of the research, is that we ran thousands and thousands of trials and started out random, and the input for that crane converged to a ZV-shaped input. It's quite an interesting result for us. So I'll post an example of that along to the website in the next day or so you can check that out and understand how to do this. It's pretty cool. I think it's something to think about reading up on and adding to your kind of controls toolbox. It's, I think, going to be really useful. So with that, I'd like to thank all of you guys for coming here the last couple of days. I know it's your vacation. You should be home somewhere maybe having fun, but hopefully this was fun and hopefully you learned something. So thank you for your attention and thank you for having me.